Look at how we have built networks for the last 30 years. We take fluid applications and force them to conform to a rigid physical infrastructure of cables, IP addresses, and static VLANs. Because the hardware topology dictates the design, security policies often end up as accidental byproducts of where a server happens to be plugged in. You end up with sprawling access control lists and operational bottlenecks just to keep basic services running. Cisco ACI approaches this problem from the opposite direction. Instead of letting the cables dictate the network, ACI relies on a logical policy model. It is a system built to take the intent of an application and translate that directly into network behavior. To make this system work, network engineers have to leave behind legacy definitions. You drop the hardware-first mindset and learn to operate a vertical stack of logical constructs. Mastering this specific chain of logical objects is the only way an operator can escape the physical restrictions of the past. It is how you build a data center that responds to what the software needs. This diagram shows the top of the ACI stack, a top-level block called the tenant, the broadest policy container. Inside, ACI slots a VRF, serving as the actual Layer 3 routing boundary. The tenant provides administrative isolation, while the VRF provides routing isolation. Separating these two functions solves a major design headache. It allows network teams to maintain specific organizational ownership without creating complex route leaking problems in the process. By decoupling the administrative container from the routing domain, ACI frees network architects from compromising their security posture to fit a corporate organizational chart. Moving down the stack, this diagram shows the VRF block receiving a new internal layer called the bridge domain. This is where ACI defines the Layer 2 forwarding environment and the gateway subnet behavior. In legacy environments, the VLAN is the full Layer 2 domain. In ACI, the VLAN no longer plays that role. VLANs are now merely edge identifiers sitting at the fabric's perimeter, acting as simple tags to classify traffic as it enters. Once that traffic is inside, the bridge domain takes over the internal forwarding work. It handles the routing lookups and broadcast traffic, scaling across the entire fabric without the strict numerical limitations of traditional VLANs. Elevating Layer 2 control from perimeter VLAN tags to a centralized bridge domain resolves the scaling constraints that restrict legacy networks. Inside the bridge domain, an application profile acts as an organizational wrapper. It holds endpoint groups, or EPGs, the network's primary segmentation units. ACI's core security rule applies here. Endpoints within the same EPG can communicate freely, but traffic between different EPGs is instantly blocked. That default block is absolute, applying even if two EPGs share the exact same bridge domain or subnet. To allow traffic between different groups, you must create a contract. These explicit filters and rules dictate exactly what communication is permitted to cross the barrier. Access is no longer granted because two servers share physical proximity on a subnet. ACI enforces a default deny posture, where every connection relies on identity groups and explicit allow lists. This blueprint lays out the completed vertical stack. The tenant holds policy, VRF defines routing, bridge domain controls Layer 2, application profile groups workloads, EPG secures endpoints, and the contract permits traffic. They work together as a single translation engine. Because every networking job is compartmentalized into its own logical object, troubleshooting follows a specific sequence. It is no longer a matter of tracing physical cables or reading port configurations. Instead, operators follow a step-by-step process. Check endpoint learning at the edge, verify domain association in the middle, and confirm contracts governing traffic flow. Architects can use broad policy objects like these any to quickly apply rules across a whole VRF, saving switch memory and simplifying the setup. But that shortcut introduces policy inheritance trade-offs that operators must manage to ensure they do not accidentally permit unwanted traffic. Cisco ACI's logical constructs replace the accidental architecture of legacy networks. By organizing the fabric into precise containers and security groups, the network becomes an intentional environment, driven entirely by the requirements of the application.